Continue on Physical Chemistry, Chapter 19, Section 5. Now let's talk about experimental evidence for electron or nuclear spin. So one was the Stern-Golach experiment in 1921. Oh, that's pronounced Stern because it's German. So that's hydrogen atoms through a magnetic field. Two, NMR and ESR spectroscopy. NMR is nuclear magnetic resonance. NMR uses nuclear spin. ESR is electron spin resonance. Obviously ESR would use electron spin. 3. The fine structure splittings of atomic spectra. 4. The degeneracy of the excited states of atoms and molecules. And 5. The anomalous Zeeman effect, where the energy of the electron is in a magnetic field. So let's talk about spin angular momentum. We have S and SZ, where SZ is the Z component of S. This would be, we're going to use cursive lowercase s here for lowercase s. So we have S's value of S is equal to S times S plus 1 times H bar, where S can be 0, 1, or 2, or 3, or S can be 1/2, 3/2, or 5/2. So this S here, the lowercase s, is the spin angular momentum quantum number. Now, if S is 1/2, then MS is equal to minus 1/2 or positive 1/2. So for SZ, we get MS H bar, and MS is minus S all the way to positive S. MS is, therefore would be like minus S plus 1, etc., to S minus 1 to S. Now remember, for L we had ML, or just M, and for S we had MS, or just M. So let's talk about, for an electron, S is equal to 1/2. So MS can be plus 1/2 or minus 1/2. Notice I said plus 1/2 or minus 1/2. So that gives us two S plus 1 orientations. So we get 2 times 1/2 plus 1, so that gives us two orientations. So the absolute value of S here, square root of 1/2 times 1/2 plus 1 times H barred, which gives us square root of 3/4 times H barred. So here's Z, so it could be 0 plus 1/2 H bar minus 1/2 H bar. So we get MS is plus 1/2 or MS minus 1/2. So the magnitude of this vector is square root of 3/4 H barred, but the magnitude of this vector is the same, square root of 3/4 H barred. Now all electrons have spin 1/2. Now photons have a spin of 1, like polarized light. So alpha would be the spin function, so we get alpha is a function of this, a W, or omega. Omega is the hypothetical internal coordinate. And then beta is the spin function. Beta is also a function of omega. So MS is equal to 1/2, therefore it goes to alpha. And MS is equal to minus 1/2, that goes to beta. So alpha is alpha spin function, beta is beta spin function. So we get psi of function of xyz, that's a spatial wave function. Like we get psi of 1s times alpha, we get 1s alpha. So that's the spin orbital and the wave function, spin orbital wave function. And then psi of 1s times beta, that's 1s beta, that's the spin orbital wave function. See handout figure 84. And that's all for section 5.